All right, so today we're just going to be talking about coordinate geometry. And that's essentially the idea of doing geometry, except we're going to use coordinates to solve geometry problems. And what this does is it kind of makes geometry problems almost more algebraic and more computational rather than a more synthetic approach, which would be using things like the basic theorems that we talked about in the previous section. And so, yeah, let's get started. So to start, we need to know exactly how we're going to assign coordinates. So there are many different ways of assigning coordinates to some kind of plane, but the way that we're going to talk about today is using Cartesian coordinates, which are essentially, they work as follows. So the way that Cartesian coordinates work is we have something called the Cartesian coordinate plane. And this Cartesian coordinate plane is essentially a way of assigning these coordinates to the points on this plane. And a plane is just a flat surface. So you can think of it almost as a completely flat, infinitely thin surface. So it's almost a two-dimensional version of the number line. So let's look at how this works. So let's say we have some point over here on this plane. Oops. Okay, so let's say we have a point here on this plane. Then what if we want to figure out where this point is? Then what we would do is we would assign it a coordinate. So this coordinate looks like this. We draw parentheses, and then we have an x and a y, and then we draw closing parentheses, and that represents a coordinate. So this first number in the parentheses represents how much the number it corresponds to on the x-axis. So there are two axes on the Cartesian coordinate plane. So here you can see that this is almost like a real number line. You can see this is like one real number line, and then this is another real number line. And these two number lines are essentially our axes, and they define where everything is. And notice that they meet at a right angle. So this is a right angle here. Okay, oops. Okay, so we call this horizontal axis the x-axis, and we call this vertical axis the y-axis. Okay, so this first number in the parentheses is how far the point is on the x-axis. So if we draw a line from the point on x-axis, we can see that it corresponds to 3. So the first coordinate in the pair would be 3. Next, if we look at the y-coordinate, it's also 3. So the y-coordinate would also be 3. And this point is at the location or coordinate 3, 3. So let's do another one quickly. Let's say this point over here. Well, we can draw where it is on the axis. It corresponds to -1 on the x-axis. So it has a first coordinate of -1, and it corresponds to -3 on the y-axis. So its y-coordinate is -3. And so its coordinates would just be -1, -3. So that's how we assign coordinates. Okay, so the first thing that we're going to talk about is lines. So let's go into lines. So lines in coordinates, we're going to describe them with 3 different things, at most 3 different things. We're not going to use all 3 of them, but in every way that we're looking at them. But let's take a look at these 2 things. So first there's slope, and that tells us how steep a line is. So one moment. Okay, sorry about that. Let's go back to it. Okay, so let's talk about slope. So first of all, the slope tells us how steep something is, or a line is. So slope of 0 would just be a flat line, maybe, or not a flat line, but it doesn't rise. So this kind of looks like it goes up, but a line of slope 0 would be perfectly horizontal. So for example, the x-axis is actually a line of slope 0. Now, as we increase how steep this line is, the slope goes up and up. So for example, this line has a bigger slope than this line. This line over here has a bigger slope than this line, and this line has a bigger slope than this line. So how do we define what a slope is more mathematically? So the way that we do that is by actually defining a slope to be the rise or change in x over the rise or change in y over the run or change in x. So we would say that the slope is equal to delta y over delta x. So that might seem a bit weird. So another way to write it is if we have 2 points on the line, y1, x1, y1, and x2, y2. These are 2 points on a line. Then the slope is equal to y2 minus y1 over x2 minus x1. So that is how we define slope. So now let's talk about x-intercept. So we just saw our Cartesian coordinate plane. I'm going to draw the plane right here. This is our x-axis and this is our y-axis. So let's say we have some line. We already figured out what the slope is. So now let's figure out what the x-intercept and y-intercept are. The y-intercept is going to be where the line intersects the y-axis. So here, this would be the y-intercept, where the line intersects the y-axis. And here, this would be the x-intercept, where the line intersects the x-axis. So these 3 things are important for our next equations for lines. So let's discuss how we would write equations for lines. So we have 3 different ways of representing lines, or 3 different ways that we generally use to represent lines. The first is something called standard form. So here we would represent lines in this form, ax plus by equals c. So what this means is that if we have a point x1, y1, then it's on the line if and only if ax1 plus by1 equals c. So that's why we write this equation. So if we have this equation, then we know which points in the plane are on the line and which points are not on the line. So specifically, we have some constraints for standard form. A, B, and C are going to be integers, and A is positive. Well, this is just generally how we would write it. Well, generally we have A is positive, but if you had real numbers, you wouldn't necessarily have to have A, B, and C be integers. But also, if we have this standard form, we can actually find the x and y intercepts really quickly just by finding c divided by a and c divided by b. So why does this work? So if we look at the x and y intercepts, here's a plane and a line. Notice that this y-intercept is going to happen when x is equal to 0. So the y-intercept looks like 0, comma something. And the x-intercept happens when the y is equal to 0. So it looks like something, comma 0. So if we plug this into the line equation to figure out what that something is, let's say the y-intercept is 0, y1, and the x-intercept is x1, 0. Then the x-intercept is going to just be, it has to be on the line. So we're just going to see that a x1 plus b times 0 equals c. So x1 is equal to c divided by a. And similarly, we can do the same thing to find the y-intercept. So you would get that a times 0 plus b times y1 is equal to c. So y1 is equal to c divided by b. So that's why we can get the x and y intercepts to be c over a and c over b. So now let's talk about slope intercept form. This is the second main form that we would use to represent lines. So here we would represent a line as y equals mx plus b, where m is going to be the slope of our line and b is the y-intercept. So y is just like, again, we're just going to represent y as some number on the y, not on the y-axis, but some y value for a point. And the x is going to be the x value for the point. So if we have a point, x and y are going to be the how much or how far they are on the x and y axes. And then that satisfies this relationship if it's on the line. Okay, next, point slope form. Here we would represent lines as y, or first, if we had a point, if we wanted to use point slope form, we generally use this when we have the slope and we have some point x1, y1. If we have a slope and a point, then we can write this equation to get an equation for the line. And that is y minus y1 is equal to m times x minus x1. And you might see that this is essentially, this is essentially the same thing that we wrote for slope. M is equal to y minus y1 over x minus x1. It kind of looks like the same thing. And the reason, or the way that you might see this differently, we'll see after we do transformations. So when we do transformations and translations, you might see how this, you could arrive by translating a line that's of the form y equals mx. Okay, so now let's go to parallel and perpendicular lines. So lines can be parallel, they can be perpendicular, or they can be neither parallel or perpendicular. But parallel and perpendicular lines can be very useful in geometry problems. So in coordinate geometry, lines that are parallel will have the same slope. So if we have two lines, y equals m1 x plus b1 and y equals m2 x plus b2, they're going to be parallel if m1 is equal to m2. So what if they were perpendicular? If they were perpendicular, then what happens is we have m1 is equal to negative 1 over m2. So the slopes are negative reciprocals of each other. Okay, so let's get into transformations. So the first transformation that's important is translation. So the big idea with translation is that if we want to move or translate some figure or some shape on the coordinate plane by a certain amount in a certain direction, then we can break down that direction into an x and a y amount, or a direction, an amount in the x direction and then an amount in the y direction. So essentially, all we need to know is how to translate certain objects a certain amount of the x direction or in the y direction. So the idea is, if we want to translate something in the positive direction for either of the axes, we just have to subtract the amount that we want to translate from the variable for that direction. So we can see this through examples, and we'll see that in a moment. And to translate in the negative direction, we just add the amount to the variable for that direction. And then an idea with translation is that we can actually shift or translate everything in the plane so that we can assign a certain point to the origin. So what that does is it preserves everything else in our diagram. So it can make computations easier sometimes, and it might make things easier to think about as well. So let's start with some examples. So the first example is translating the line y equals 2x plus 1 to the right by 3. So this is pretty simple. All we're going to do is we want to move it to the right. Right is the positive direction. So if you look at the coordinate plane, going right is the positive direction. So we're going to subtract from x. So we're going to change x to x minus 3. So now if we have this equation, our new equation is going to be 2 times x minus 3 plus 1. And when we simplify, we just get 2x minus 6 plus 1, or 2x minus 5. So that would be our new equation, which is shifted to the right by 3. Next, let's translate this line y equals 2x plus 1 down by 4. So in this case, we want to move down, which is in the negative direction. So you can see it's negative. So if we're moving in the negative direction, we're going to add 4 to the variable. So y would become y plus 4. And because of that, we get y plus 4 is equal to 2x plus 1. And in other words, y equals 2x minus 3. Another way to think about this is you can just think of, we already have everything solved for solved for y. So shifting down by 4 is the same thing as just subtracting 4 from all the y values. So when we subtract 4, we just get 2x minus 3. Each is the same idea, essentially. And now you might be also able to see how this equation, this point slope form, is essentially taking this line of y equals mx and translating it so that we translated x1 and y1 in the positive directions, or depending on whether x1 and y1 are positive, they're going to be positive or negative. But you're essentially shifting this line y equals mx in the point slope form. And that's another way to think about it. So now let's talk about rotation. So rotation is kind of difficult in the Cartesian coordinate plane because we simply can't rotate easily. Everything is more rectangular. So if we rotate, the easiest way to rotate is by a multiple of 90 degrees. So what we would do to rotate by 90 degrees is, so for example, let's say we have our coordinate plane and we have some line. For simplicity, I'm just going to draw it through the origin, or that's not through the origin, but that's pretty close. And let's say we want to rotate it by 90 degrees through the origin. In that case, all we have to do is find this new line that's 90 degrees to the original line. But then we already know what this line slope is because we already talked about perpendicular lines. So if these two lines are perpendicular, and this line was y equals mx or it's just y equals mx because the y-intercept is 0, then this line must be y equals negative 1 over mx. So you can see how, since we can write equations for perpendicular lines pretty easily, we can actually do rotation by 90 degrees pretty easily. So let's say we have a line with slope m passing through a point x1, y1. Then if we want to rotate that line by 90 degrees through x1, y1, then since the new line will have slope negative 1 over m, and it has to pass through that point, x1, y1, we get immediately, using point slope form, we get this equation for the new line. So let's get through some examples. So first, let's rotate the line, y equals 3x plus 4 by 90 degrees. So you might notice that there's something missing from this problem, and that's a point. So let's actually pick a random point. It doesn't really matter which point, but let's choose a point that's on the line. to make things easier. You can rotate about points that aren't on the line, but it's a bit more difficult. And you would essentially have to do this rotation twice with 2 points on the line, rotate them 90 degrees, and then find the new line through those 2 points. But let's just rotate this line, y equals 3x plus 4, through the point 0, 4, which is just the y-intercept. Okay, so if we rotate this by 90 degrees through that point, then essentially, let's draw a picture first of all. We have the line looks something like this. And in the end, our new line is going to look something like this, where it's perpendicular to the original line. So our new slope is going to be the negative reciprocal of the original slope. So negative 1/3. And the y-intercept is going to be the same because, or it's going to pass through 0, 4. So we already know the y-intercept. So our new line is just going to be negative 1/3 x plus 4. So that would be the result when we rotate y equals 3x plus 4 by 90 degrees through this point 0, 4. Oh yeah, also Mason is here, so you can ask any questions if you have any questions. And just send him a message. Okay, so now let's look at this next problem, which is rotating the point 2, 3 by 90 degrees clockwise with respect to the origin. So if we draw our coordinate plane, two, 3 might be, or let's label our axis 1, 2, 3, and maybe 1, 2, 3. This isn't really to scale, but either way, we have this point 2, 3. And now we're going to rotate it 90 degrees clockwise with respect to the origin. So if we draw this dotted imaginary line, after we rotate it, it's going to go 90 degrees to this new point, or actually, I'll draw a picture that's more realistic, to this new point somewhere. And you can tell where this point is already because of the way I drew it, but we'll figure out how we can realize that in 2 different ways. So we just rotated it 90 degrees and it landed on this new point. So how do we figure out where it is? So what was our original line through the origin? So essentially, we're taking this line that was through the origin and rotating it by 90 degrees, and then finding this new point that's the same distance from the origin. And you have to remember the Pythagorean theorem that we talked about before for finding distance. So let's quickly do that. This original line was just y equals mx plus b. That's our general line, but the b is equal to 0 because it passes through the origin. And m is just going to be rise over run, or 3/2. So our line, our original line, was 3/2 x. And then we rotated it by 90 degrees with respect to the origin. So we already know how that works. We have our new line is going to be perpendicular to the original line. And since it passes through the origin, it's just going to be negative 2/3 x. Now we want to find this point on the line that's the same distance as this original point. And we know that it's going to be in this fourth quadrant. So it's going to have a positive x and a negative y. So if we have a positive x and a negative y, then we want to find this point with the same distance as this original point. And since this slope is just a negative reciprocal, notice that when we have 3, negative 2 as our point, since these two numbers are equal in magnitude, when we've used the Pythagorean theorem to find the distances from the origin, we're going to get the same thing. like this is going to be the square root of 3 squared plus 2 squared. And this is going to be the square root of 3 squared plus negative 2 squared. So the point 2, 3 just maps to the point 3, negative 2 when we rotate it 90 degrees clockwise about the origin. So notice how we just took this point that was of the form x, y, and it almost looks like what we did is we went to y negative x. And in fact, that's basically what happened. So if we try to generalize this, if we have a point x1, y1, and it's rotated 90 degrees clockwise, then we're going to go from xy to y negative x. Or that's essentially what we got here. And now what if we went the other way, counterclockwise? If we went counterclockwise, then we're essentially choosing a negative value of x. So we're going to, in this problem, we would have got negative 3, 2. And it's, again, the same distance from the origin because these numbers are equal in magnitude to the original numbers. So if we went counterclockwise, we would have gone from xy to negative yx. So clockwise would be this, and counterclockwise of 90 for 90 degrees, we would be going from xy to negative yx. Now, what about a 180-degree turn with respect to the origin? And this isn't counterclockwise or clockwise because they're the same thing. And if we went 180 degrees, then it's essentially the same as reflecting it across the origin. So what happens when we reflect across the origin? It's just going to go in the exact opposite direction for x and the exact opposite direction for y. So it's going to be negative x comma negative y. So xy would just go to negative x, negative y. So that's our basic rotations. So let's go into reflection. So reflection is also a bit tricky, but it's doable. So reflection is, with respect to a point, is essentially the same as rotating with respect to that point by 180 degrees. So if you look at this point over here, the origin, and we have this point here, reflecting this point over the origin will just give us this other point, which is on the opposite side of the origin. All three of these points are collinear, or they lie on the same line. And this origin, which was the center of reflection, is going to be the midpoint of this line segment. So the same idea we can state by just saying that we're taking this point and rotating it 180 degrees. It's the same thing. They're the exact same transformation. Or not the exact same, but for a point, they are the exact same. So on the other hand, if we had to reflect across other geometric figures, it's kind of tedious, but we can also reflect across lines. So we'll talk about that in a bit. But first, let's go over some simple reflections. So first, we can reflect a point about the origin. We already talked about that essentially because we talked about rotating 180 degrees across the origin with respect to the origin, which is the same transformation. Next, what about reflecting a point about the x-axis? Well, if we draw it out, then we have this point xy. And when we reflect it across the x-axis, it's just going to go to the other side of the x-axis, and its y direction, or its y coordinate, is essentially going to swap signs. So xy would go to x negative y. And the same thing happens when we reflect across the y-axis. So the x coordinate is just going to swap signs. we're going to go from xy to negative xy. So now, what if we want to reflect about the line y equals x? This is also not, this is an interesting transformation. It's not very tedious. So if we have some point xy, or I'll call it x1, y1, and we have this line y equals x, then when we reflect across this line, so when we reflect across lines, we have to find the point on the line that's closest to this point that we're reflecting, and then reflect it across the point. So this new point is actually going to have coordinates y comma x. And similarly, if we had y equals negative x, which is kind of similar in that they have slope of magnitude 1, then when we reflect this point across this line, the new point is going to be negative y negative x. So one thing you might notice is that both of these two reflections are actually they are reflections across the origin. So yx is the same as negative y negative x reflected about the origin. So that's just something interesting to note. So another, like, essentially these four reflections, when we reflect negative y negative x across this y equals x line again, then these four reflections will actually just form this essentially this rectangle or parallelogram with center of this origin. And so now let's talk about reflecting across lines. So we just talked about this, but if we want to reflect a point across a line, then we need to find the point closest on the line, closest to the point that we want to reflect. And then we reflect it across that point. So let's try an example. So find the resulting point when 3, 5 is reflected about y equals 2x. So if we draw our coordinate plane, y equals 2x looks, or it passes through the origin, and it looks kind of like this. That's probably a bit too steep, or we haven't really defined any units for our axes, so it's not a big deal. It's not to scale. Then we have some point 3, 5 over here. Now, when we reflect this point 3, 5 over this line y equals 2x, the idea is that we need to find the point closest to this point on the line. So the way that we do this is, remember that the shortest distance from a point to the line is this perpendicular distance. So this distance is going to be perpendicular. And we know that if it is perpendicular, this line between these 2 points is perpendicular to this original line, y equals 2x. So we can find the equation for this line, and then use that equation to figure out what this point is. So how we do that is as follows. We know that this line is perpendicular to y equals 2x. So its slope m is going to be negative 1 over 2, or the negative reciprocal of this slope. So it's going to be negative 1 over 2x plus b, or our equation is going to be negative 1 over 2x plus b. But rather than use that form, we can also just use point slope form. So, and then solve for this y-intercept form. So our point is 3, 5, because we want the line to pass through 3, 5, and our slope is negative half. So our line is going to be y minus 5 is equal to negative half times x minus 3. And so now let's solve for slope-intercept form, because our original, this line is also in slope-intercept form. And when we solve our set of equations, it'll be easier if they're both in slope-intercept form. So if we simplify this, we get y minus 5 is equal to negative half x plus 3 halves. And then y equals negative half x plus 10 over 2, so 13 over 2. So this is our equation for the line. And you might notice that this is already really messy. And that tends to happen in coordinate geometry. Everything kind of ends up being weird fractions. These aren't too bad, but yeah. So we have this line y equals negative half x plus 13 over 2. And we have this other line y equals 2x. And the point that we want is the intersection between these 2 points, two lines. So if we take these 2 lines, their intersection, we can find that just by solving the system of equations. So we get 2x equals negative half x plus 13 over 2, which means that 5 half x is equal to 13 over 2. So x is equal to 13 over 5. So now that we have x, we can simply plug back in to find y equals 26 over 5. So now that we have that, we know that this point is going to be 13 over 5, 26 over 5. So with that, we can now find what this new or this reflection is. So the way that we do that is we notice that this red point is the midpoint of this segment connecting those two. So if we take the amount that we go up here and to the left here, and then we add that to the midpoint, we should get to our left point. So what this means, I'll draw a bigger picture here. We have this point 13, 5, comma 26 over 5, and 3, 5. So here, the rise would be 13 over 5 minus 3, which is, or this is actually a drop, or it goes negative, but this would be negative 2 over 5. And then the amount that we go to the right by is going to be 26 over 5, or 5 minus 26 over 5, which would be, or actually, this is to the right. So actually, what would happen, actually, this figure isn't exactly realistic or drawn to scale, but this would be negative 1/5. So if we want to get to this point, we would just have to do the same addition to this point to get to this point. So we can just reverse it. So our original point was, so our original point would be, so this was 15, so this would be 11 over 5, comma 27 over 5. And so that would be our reflection. So let's just do this again, except with a different problem. So now we want to find the resulting point when 3, 5 is reflected about y equals negative 3x plus 3. Actually, since this problem is the exact same idea, I think we'll skip this one and we'll go to dilation and maybe come back to this at the end if we have more time. So let's go to dilation. So essentially, dilation is the idea of multiplying by a scale factor or scaling a certain situation. So dilation in Cartesian coordinates and in general is most easily done when we have to dilate about the origin, because then we can just move our points by just multiplying all our points by some constant k, which is our factor. So for this reason, it might be easier to actually just move the origin by translating everything to a certain point, to the point where our center of dilation, and then moving back after. So let's go through some examples. So find the resulting point when 3, 5 is dilated with respect to the origin by a factor of 4. So in this case, we have 3, 5. And remember that if we dilate with respect to the origin, xy just goes to kx, ky, where k was the factor. And here our factor is 4, so 3, 5 is going to go to 12, 20. So that was pretty simple. Next, we need to find the resulting point when 3, 5 is dilated with respect to the 0.27 by a factor of 3. So here, we can actually do this by moving this origin to 2, 7. So what I mean is, so if we draw our coordinate plane, actually, let's not draw this to scale either. This would be 3, 7, 3, 5. And this might be 2, 7. So there's two ways to think about this. We can think of just dilating it with respect to this point, which is a bit harder to think about. Or we can think of just pretending that this is our origin. So let's pretend that this is our origin 0, 0. In which case, this point, if we translate it the same way, is going to go to 1, negative 2. Then we can just scale like normal. Our factor is 3, so 1, negative 2 would go to 3, negative 6. And then we can just go back. So we know that we were pretending that this was 0, 0 by subtracting 2 from the x coordinate and subtracting 7 from the y coordinate. So we can just add 2 back to the x coordinate and add 7 back to the y coordinate to get our result, which is simply 5, 1. So that's probably the easiest way to think about dilation with respect to points that aren't the origin. So now we know that when we dilate, the resulting point would be 5, 1. So now find the resulting point when 3, 5 is dilated with respect to the 0.27 by a factor of negative 3. So if we are doing negative 3, notice that if we have a point and we dilate it by some factor with respect to this red point actually. So if we have this red point and this black point, and we dilate this black point with respect to the red point by some factor k, so it goes here. Now, what if we dilated it by a factor of negative k? Then essentially we're going in the opposite direction, but by the same amount. So what this means is that this point and this point are reflections of each other, or this point and this point are reflections of each other across this red point. So if you remember from the last point problem, we had 5, 1 as our resulting point when we dilated with respect to 2, 7. So 5, 1, oops, I'll use black again. 5, 1 is one of the endpoints of the segment that has midpoint 2, 7. So what that means is that the other point is just going to be negative 1, 13. And the reason is what we want is these 2 points to satisfy that this middle point is the midpoint of the 2 endpoints. So we could just use the midpoint to find the other endpoint. So in other words, we didn't have to do any dilating here since we already did that work here. If we dilate by a factor of negative 3, it's just going to be the reflection across 2, 7. So we know that it's negative 1, 13. So again, what is the relationship between the 2 points in the previous examples? They're just reflections across the center of dilation. I'll just write reflections, but they are reflections across the center of dilation. So now let's talk about areas. So there are 2 main theorems that we'll discuss today in coordinate geometry to find areas. And the first one is going to be the Shoelace theorem. So Shoelace's theorem is a really cool theorem that you can use to find the area of a convex polygon with certain vertices. So these vertices, let's call them A1, B1, A2, B2, all the way to A and Bn. And they have to be listed in order either clockwise or counterclockwise. So then we can find the area just by evaluating this expression. A is equal to half A1 B2 plus A2 B3 plus so on until A and B1 minus B1 A2 plus B2 A3 so on until B and A1. And that looks really complicated, but we'll see how this is actually not too complicated to think about in the next example and why it's called the shoelace theorem. So let's look at an example. What is the area of a triangle with points or vertices 2, 4, 6, 3, and 0, 0? So for shoelaces theorem, what we can actually do is we can list these points in order. So let's first draw a picture. We have 0, 0, and then we have 2, 4 is going to be somewhere here, and then 6, 3 is going to be somewhere here. So our triangle looks something like this. Now, for a triangle, we can use any order because regardless of which way we go around the triangle, it's going to be counterclockwise or clockwise. But what we can do is actually list the coordinates like this: 2, 4, 6, 3, 0, 0, and 2, 4. And now we can essentially, to get this formula, rather than thinking about it algebraically like this, which might be a bit hard to think about, you can actually do it like this. Let's color it or draw lines, diagonal lines like this, and then more diagonal lines like this, red lines this one. So what we're going to do is any two numbers that are connected by a line, we're going to multiply them. And if it's a black line, we're going to add it to the sum. And if it's a red line, we're going to subtract it from the sum. So essentially what this is 2 times 3 is 6, plus 6 times 0 is 0, plus 0 times 4 is 0. And then we're going to start subtracting the ones that are connected by red lines. So 6 times 4 is 24. 0 times 3 is 0. And 2 times 0 is 0. So when we do that, we get our answer of -18. But this isn't the area of the triangle. This is just this inside part over here. To find the area, we have to take the absolute value and then divide by 2. So if we do that, we get our answer of 9. So let's do another example. This one isn't a triangle. So if we have the coordinate plane and a square with endpoints 2, 0, 0, 2, -2, 0, and 0, -2, it's going to look like this. And then we have this line x equals 1, and it's going to cut the square into 2 pieces. So we want to find the area of this larger piece over here. So this is actually pretty simple because we know the coordinates of these 2 points. This is 1, 1, and this is -1, -1. Or wait, this is not -1, -1. This is 1, -1. So now that we have those 2 points, and we also have these points, 0, 2, -2, 0, and 0, -2, we can just use shoelaces theorem. So if we write the points in order, -2, 0, 0, 2, 1, 1, 1, -1, 0, -2. And then finally, we have to repeat the first point. So we write -2, 0. And then we draw our lines, or we can also call them, I guess, shoelaces. So then we can just do the multiplication. So -4 plus 0 plus -1 plus -2 plus 0 minus 0 minus 2 minus 1 minus 0 minus 4. And if we do this, -4, -5, -7, and then we're going to subtract 2, 3. So negative 14. Then we have to take the absolute value and half it. So we get our answer of 7. You could also do this without a coordinate or without coordinates, but that might be a bit tougher. Or it wouldn't be too much harder, but coordinates with shoelace is pretty simple and easy to think about. So now let's talk about Pick's theorem. So if we have a polygon, all of whose vertices are lattice points on a coordinate plane, and I is the number of lattice points that are inside the polygon, and B is the number of lattice points that are on the boundary of the polygon, then Pick's theorem actually tells us the area in terms of I and B. It says that A is equal to I plus half B minus 1. So this is actually pretty interesting because we just have to look at the diagram and look at how many lattice points are inside and on a figure, and we can instantly find the area. And it doesn't show up too frequently, but when it does show up, this formula can be super, super easy to use and really important. So let's apply it. So again, Pick's theorem states that A is equal to I plus B over 2 minus 1. So let's find I. I is the number, or first let's read the problem probably. A triangle with vertices A equals 1/3, 1/3, B equals 5/1, and C equals 4/4 is plotted on a 6 times 5 grid. What is the fraction of the grid that is covered by the triangle? So if we, and this is from the 2015 AMC8. So if we look at this grid, we have this triangle and then we have the grid. We know how big the grid is. It's just 6 by 5. So the area of the grid is 30. Now let's find the area of the triangle. So let's start, we're going to use Pick's theorem. So let's start by finding the number of points on the interior of the triangle. Well, there's 1 here, 2, 3, 4 points on the interior of this triangle. And then, so we know that I equals 4. And then for B, for boundary points, there's 1, 2, 3, and then there's this 4th point that's also on the boundary. So B is also equal to 4. So now when we plug this in, our area is just going to be 4 plus 4 over 2 minus 1, which is 4 plus 2 minus 1, or 5. So what we have to actually go back and read the problem, which is what fraction of the grid is covered by the triangle. And that's just going to be 5 over the entire grid, which is 30, which gives us 1/6. And that's our answer. So that was a pretty simple application of Pick's theorem. And we're basically out of time. But yeah, we're basically out of time. So let's not do that last reflection problem. It's essentially the same idea. And there were also 2 additional examples that we didn't exactly have time for, but that's fine. They were kind of extra examples. So yeah, that's it for today. So if anyone has any questions, you can ask them now. And also with the next lecture is going to be next Wednesday. So it's going to be on recursion. So make sure to come to that if you're interested. And then solutions will be posted for solutions for the last handout are already posted. And solutions for this handout will be posted before the next meeting. So when you're done with the review of problems, you can check. And that's essentially it. So I hope you enjoyed. If you have any questions, you can ask them. And other than that, thank you guys for coming. We'll see you next week.
Thank you. Bye.
Bye. Oh yeah, I'll stop there.